to have you all here with us to attend the 24th National Conference on Communications. And we do hope that you have a great experience here at IIT-Hyderabad. We are going to kick off our first set of tutorials this morning at 9:30. Our speaker for this tutorial is Dr. Abhishek Gupta from IIT Kanpur. And we will have a short break at 11:10, and we will come back here at 11:40. So this session goes from 9:30 to 12:40. Okay, so that's about the session, and we kindly request you all to put your mobiles on silent mode so it doesn't bother the speaker and the rest of the audience. Again, I would like to very warmly welcome our tutorial speaker for today, Dr. Abhishek Gupta. Dr. Gupta received his dual degree BTech MTech from IIT Kanpur in 2010 and his PhD in electrical and computer engineering from the University of Texas at Austin. He is currently an assistant professor of electrical engineering at the Indian Institute of Technology, Kanpur. His research interests include wireless communication, stochastic geometry, and numerical methods. And he's a recipient of a number of awards, including the GE FS Leadership Award by General Electric and the Institute of International Education in 2009. And he's received the IIT Kanpur Academic Excellence Award for 4 consecutive years. He's also the author of books, specifically MATLAB by Examples and Numerical Methods in MATLAB by Finch and Springer A-Press. And he's also had stints in the industry as a senior standards engineer at Samsung Research in Dallas with Applied Microelectronic Circuits Corporation in Pune, FutureY Technologies in New Jersey, and Nokia Networks in Illinois. So with this brief introduction, I will not keep you from the speaker today. Again, a very, very warm welcome to all of you. And with this, I would hand off to our speaker, Dr. Abhishek Gupta.
Thank you. Thank you for the introduction. This is the first talk, 8 o'clock. So thanks for coming. This talk is mainly about millimeter wave, and we are mainly going to focus on stochastic geometry based application, like how we can analyze those systems. So let me start with it. So basically we have seen that in past we have been mainly focusing around 900 megahertz frequency for cellular operation. Okay, and people have used a lot of other techniques, for example, to increase the spectral efficiency, and like they have densified the network to get more and more cell splitting gain. But eventually we found out that it's kind of saturating. So one way to increase data rate is to actually go up in the frequency, because then you can have lots of spectrum, and that is why this millimeter wave becomes so promising. There is a frequency band around 24 gigahertz to 100 gigahertz, which we call millimeter wave because of its wavelength. It's in the range of millimeters. And in past, it was thought that it's being used in past also for different other applications other than the communication and specifically cellular. People always thought that it doesn't have very nice propagation characteristics. You cannot have a cellular deployment, reliable deployment. So people ignored it in the past. But recently, due to recent development in industry and academics both, we found that it's not that bad. And so few frequency which we looked at generally, people are looking at this 24 gigahertz band. There's like 3-4 gigahertz there, and 38 gigahertz bands, around 1.4 gigahertz there, and around from 657 to 671, that is 14 gigahertz band there. So there are some issues with millimeter wave, and that is what it delayed the cellular deployment of millimeter wave, but it also is a little bit beneficial for us as we look at. So for example, first feature of millimeter wave is its sensitivity to blocking. Millimeter wave is severely impacted by different blockages, for example, buildings, or it can be even blocked by the people. If you have if the other person is standing between you and the base station, there can be approximately 20 dB loss in the signal, which is huge for this. Then you can even block by your own hands, right? If you're keeping a phone like this, your hand can block the signal. And of course, the whole body can block it. For example, if you look at the number, is normal window can degrade the signals by 30 dB. A human body can degrade by 20 to 40 dB. And the main reason is because the millimeter wave cannot diffract well around the edges. It cannot penetrate the objects. And of course, it has wide bandwidth, so you have more noise power also. So what we get from this blocking is that, of course, outdoor to indoor communication may not be possible. And we do want line of sight communication. If you can get a direct link, then we are okay. But if you do not get, if you are in line of sight, the communication may not be possible. But there is a benefit to it also. When the surging base station get blocked, also the interference can get blocked. Okay, so you are not always in a bad state if you have blocking. Okay. The second factor is directional antennas. So people always, so normally you have some transmission going from transmitter to receiver, and then the aperture size of the antenna decide how much power you are absorbing at the receiver. Okay. But when you go to the millimeter wave, the antenna size of course goes by a huge amount, 1 upon lambda square. So in that case, the area of the antenna decreases, so the power it absorbs also decreases by a huge amount. So people always argued that this way you are getting less power, and that is all being captured in the Friis equation, that the power received at the receiver is actually decreases when you increase frequency. But this is not true if you keep the aperture size same as the UHF frequency. So because millimeter wave antennas are smaller, you can pack more and more antenna in the same space. And when you do that, you find that this received power at the receiver is same as what you have got in the LTE. Okay. And theoretically, of course, there will be some constraint because you are packing more antennas, so you have to do synchronization between different antenna array elements. There will be some penalty for that also. But then there is a benefit that you can also add antennas in the same way at the transmitter. Okay, and that will give you a gain, because this will help you focus power to the receiver, will also give you a beamforming gain in some sense. So by using millimeter wave, you are actually getting gain in the transmission power as people thought, against what people thought in the past. So beam of course need to be pointed in the right direction. They will be very narrow, and the communication will be highly directional. Okay. So what do we get from that? Since we have very highly directional antennas, the interference will again be small, because all the base stations will be pointing at their user's location, and there will be less probability that they will hit any random users. Like suppose you are somewhere and all the base stations are around it, but each one is using very narrow beams. So again there is a less probability that you will get hit by a beam, and that reduces the interference. Okay. So that is just the main issue about millimeter wave, and those are the key features. But there are of course again different issues as we see in the slides. So in part 1, this is actually this tutorial will be divided into 4 parts. First is modeling issues, modeling challenges with millimeter wave. So here we focus that what is different in millimeter wave than LTE, and how we should model those things, right? Where we should be careful about. Second part, since the analysis and the modeling is dependent on random geometry, there is a small part where I will discuss stochastic geometry. What is it, how we can apply it to our analysis, different key results from it. Then the third part is whatever we have learned from part second, we will use it to analyze a millimeter system. So there is of course a lot of paper here. So I will consider a very basic system of millimeter wave, that how we can derive things, and then there are of course a lot of following papers. And fourth part will be what we can understand from application, some examples, some insights from the analysis, what we have read. So most of the talk is based on my own paper, is again with the same name, modeling and analysis. So for references, you can also look at those papers. Let me start with part 1. So here we talk about what are different modeling challenges in millimeter wave. Okay. So first, let's take a blocking. So what happened in sub-6 GHz scenarios, that blocking can again happen because of reflection, diffraction, different penetration, shadowing, a lot of things. The tree can come in between. But since we always talked about the communication link is in meters, like in hundreds of meters, 200 meters, the base station is always at a distance from receiver in normal sub-6 GHz. Most of the communication which happened was non-line of sight. Okay. Rarely we talk about line of sight communication. All the time you are using your phone, it's inside house or somewhere you were blocked. So one way is to actually compute it correctly was doing a whole ray tracing of the environment. Or people in analysis actually talked about some models which were based on experimental data. Right, they did some measurements and then fitted a statistical model over it to compute a statistical model for analysis. The good point was that since most of the things were non-line of sight, people did not care much about differentiating the two. Like they did not distinguish the two, that this link when is line of sight, non-line of sight. People generally considered a single parallel exponent, which is greater than 3, to model all kind of links in sub-6 GHz. But this, of course, not the case in millimeter wave. As we have discussed, blocking is severe. You need to consider it. If you are in non-line of sight, this may actually lead to a total loss of signal. So you need to carefully characterize when the signal is line of sight. Okay. Plus, this blocking also reduces interference. So you need to be, if you do not consider it properly, then you get a pessimistic result because you always think the interference is large, but interference is also reduced. Okay. So, how we can characterize that a link is blocked or not, more from an analysis point of view. So, in 3GPP generally, when we talk about blocking models, we talk about a line of sight probability, that if a link, suppose there is a link of length r, then what is the probability of that link will be blocked as a function of r. So, of course, r increases, then blocking probability increases. A standard function which people generally talk about in urban scenarios like this, which I plotted it here, is like at a distance you always get a line of sight, and when after that distance your line of sight probability decreases very sharply. Okay, that is the case generally with urban. When you are at a location, at a intersection of roads, you can see some area around you without any blocking, and once you go further away than that range, then a lot of buildings, high-rise buildings comes into picture, and your blocking can decrease severely. In suburban case, people also talked about this function. This is simply that the line of sight probability is decreasing exponentially. Okay, and here this B2 can be a bit more. This means the decrease is not that sharp. And then people talked about different adaptation of this to include heights, foliage losses, and depending on different scenarios, whether it's urban, dense urban, rural, or void kind of scenario. Okay. So all these models are generally, in what we use in 3GPP, are mainly derived from fitting experimental data. So you do measurement, you fit that data, you get a model. Okay. What we are concerned about, that can we have an analytical model which can model this kind of blocking, or at least validate it what we have been using in simulation. Something this looks is a widely used this is a widely used model. So can we get something like that? And one way to use this, one way there is a motivation that these blockages and all those things are generally random. Okay. Of course, in a city they may look deterministic, but when you talk about an average performance over different cities, the user is arbitrarily located, the building's location may look random to it. So based on that, can we compute this, and can we also understand the dependence between this parameter, this BS, this is defines how sharp the blocking probability decreases. Can we derive some dependence of this over different parameters, like for example building density or building sizes? Okay. So then apart from that, we also have self-blocking, which was not in the previous case. So one way to model this can be that suppose there is this guy standing here and the phone is here. So he's looking his phone like this, right? So his body creates a block kind of blocking to him. For example, all the base stations which are in this location will be blocked by the user body if the device is at the origin. Okay. So I'm looking at it, and all the base stations directly behind me are blocked. So this kind of blocking can be modeled by a blocking code, and with some angle omega that depends on where the user device is and what is the width of a user body. Okay. Then third part is this modeling blockage correlations. Even in 3GPP model, when we always talk about independent blocking, that each link can be blocked independently, right? Which may not be the case when we talk about very network in a dense case, because if a large building is close by, it can block many signals, not just one, right? So just looking at the distance of two base stations, if they're very close, they're blocking that the blockages from the user will also be blocked. Okay, so that is also a very interesting thing, and this can also help us to understand when the user moves around the space, what is the temporal and spatial correlation of the blocking it faces over the time. For example, yeah, for example, you can look at this thing, and there are multiple base stations here, right? Either they are communicating together, or even one is communicating and the other are interfering, right? But this interference, other base station blockage is correlated. But you can also talk about that there is a single base station and one user is moving, right? Same scenario is there. So you derive two links from the same base station to the two location of the user, and you also see that those links are also blocked in correlated way. So when you are moving in a dense state, you will be in the blocked state for some time, right? So this blockages is very important to be modeled. So this is to motivate that these blockages, if you want a model, we have to consider a random deployment of blockage to understand the overall performance or average performance of the system. Second, similarly, large antenna arrays. This I said that there will be a lot of antennas at mmWave, and this will result in a directional beam. Okay, but there is a difference that in past when we talked about LTE, we had like 4 or 8 antennas maximum, right? Generally 4 antennas. So you also had 4 RF chains, one for each antenna. So the benefit is that you can do all kind of recording at the baseband, and whatever 4 signals you get, you can directly individually feed it to 4 antennas. Okay, that is fine. That is actually works very great, good. But in mmWave, you are going to have 32 to 256 antennas. Recently, AT&T did a demo, which they had a base station with 5 112 antennas in a very packed area. You cannot have those many RF chains. You cannot feed each individual antenna with a baseband signal. It requires a lot of power, and it's not feasible. So what people came up with is called analog beamforming. This means that you will have one single RF chain and you will do precoding at the RF level itself. So whatever signal you have, you will feed it to a phased array, right? This has same number of phase shifters as number of antennas, and by changing the phase of this, you can steer a beam into a particular direction. Okay? So you only have single RF chain. The problem is that, of course, you can only support single stream and single user because you are not doing any precoding at this thing. But you so what will be the resultant thing? That you will have a beam pointing in a particular direction. So to model those kind of beams, you can actually compute those. Simulation we do all those things, but for analysis, we can approximate the beam by a simple this kind of approximation. So you have some angle here 2 theta b, that is the beam angle. So actual pattern may be something like this. We approximate it by the black pattern. That in this region the gain is G1, which is the maximum gain, and in the back lobe the gain is G2. Okay. So what will result in is the gain is a random variable with two values G1 and G2. G1 with probability theta b by pi. So since when angle is theta b, the gain is G1, right? So and the angle can be from 0 to pi. So the probability that you will get a G1 gain is theta b by pi, if you assume that user is located randomly around you. Okay. The same thing can also be with UE. You can model similarly. And then we also talk about hybrid beamforming. This is the case when you do want to support multiple streams. Then the beamforming is done in two stages. One is of course the previous one, which is RF. First one is this baseband recorder. Suppose you have 4 RF chains. Then you can generate 4 symbols from it. And then those RF chains are either connected to all the antennas by a phase shifters, or they are connected to a set of antennas, right? And each signal is fed to depending on those many antennas. So what happens? The resultant pattern is a superposition of the beams, single user beams, okay, or single stream beams. And what you can get is something of this pattern. For example, if you are using 2 RF chains, you generate 2 symbols and then encoding both one, you get one beam like this and another beam like this, right? So this is of course a nice figure which shows that both beams are similar way and you can add it, but when you actually compute it from antenna array, you find these beams are not very nice because when you steer a beam, when the beam is steered at a direction in parallel to the beam, then the pattern is not that nice. But when you steer it orthogonal to the anti-array dimension, then you get a very nice beam. Okay. So those things are there already, but for some approximation, we can approximate a beam by superposition of this, and then you can to consider the impact of asymmetry of beams. That of course when you steer at a direction, so when you are pointing at 90, suppose this is the antenna array and you are pointing straight, then the beam is nice. When you point in this direction, then the beam gets distorted, right? So those can be actually taken care by this called virtual channel models. In this, the whole area is split into asymmetric regions depending on different number of beams. So you have, suppose you have n antennas, then you can quantize the whole space, 2D space around you into n different spaces. Each space corresponds to one beam. Okay. And then you can do such kind of computation over there also. But in simplistic case, it will be something like a superposition of different beams. So of course, when you say the probability of being hit by a aligned beam is again doubles here. So if it comes in this region, if the user comes in this region or this region, both where it will get a direction, the pointed beam, and the probability will be just double. The third point here is base station deployment. So this is a typical figure which shows, this is I think, yeah, this is UT Austin area, and then the star mark shows the LTE base station, and then this red are millimeter wave base stations. Here we plotted the coverage area of a millimeter wave base station, that there is also a LTE base station. And when you look at it, that earlier in previous case, when we talk about, we have very nice kind of Voronoi cells, that the whole area is divided into nice convex polygons, and then you can associate each area to a base station, right? So that's the concept of cellular, right? You have cells in that. But here when we see that these cells are very irregular shaped, they are not even continuous because of the blocking, that this building blocks the area here, but the other point is still covered, right? So in those cases, conventional Voronoi type cells are no longer valid, right? We have to talk about what kind of new cells will be there. Again, when they are deployed with LTE, so that is one thing, because even if they can provide very high data rate, it's expected that they may not be able to provide a universal coverage all the time. So you need to have some kind of LTE overlay over it to support some control, or at least provide as a backup mechanism when nothing works in millimeter wave. So how the deployment should be when you deploy it with along with LTE base station. And then the last point talks about that recently we have been, in past the companies used to buy the towers, right? They own those towers and then deploy it, right? But when these number is increasing, right, the number of base stations are increasing every day, the operators are no longer interested in buying those towers, right? So there is a rise of third-party business vendors. They're coming and putting their site towers, and then as an operator you can just lease those towers, right? So what happened that two operators can actually lease the same tower and then just put their base station on top of each other. Okay, if they're using different frequencies, it's fine. But when we talk about spectrum sharing, these two base stations can interfere to each other. Okay, so how do we actually model such kind of co-location? That some base station can be co-located, some base station are not co-located. Okay. And again, with this many base stations, the base stations are also not pre-planned in some sense. I mean, pre-planned in the sense that you have to deploy many base stations in this space, and then it is very much dependent on where the blockages are, and so the deployment itself is also becoming more and more random. Okay, so let me actually go to the next part of it. So here in this part we just talk about different kind of modeling challenges which we will face in millimeter wave. Okay, so let me start with stochastic geometry, then we will see that why we are actually using this kind of tool to analyze millimeter wave. Okay, because we will connect with all the modeling challenges we faced and how this is actually a very nice tool to be used there. Okay, so first of all, mainly we are talking about system level performance, not link level. So one parameter which will be most important here is assigner of a typical user. So you just assume a user arbitrarily located in the space, and for that user you try to compute what is the assigner it sees over the time or on the average. And then one way, because this is again random, one way to characterize it, to look at this probability coverage, assigner coverage, which is that given a threshold, what is the probability that assigner is greater than some threshold. Okay. From there you can also get rate coverage, right? There is a connection between assigner and rate, either upper bounded by Shannon formula or with some practical implications. You can always, it can be actually lower, but you can find a relation between assigner and rate, depending on what kind of modulation other things are using. And then we can also talk about area spectral efficiency, which is the number of transmission happening, number of bits being sent in a particular area. So you multiply, you get the rate, average rate, and you multiply by the transmission density, how many transmitters are happening, right? Are happening. Okay. But So how we handle in conventional models, right? If you look at, there has been in past, like it's not a new topic, so people have been working on different models of cellular, how we can get a better model for those things. For example, simplest is the Wiener model, which is the oldest one also. Here we assume the base station are in a line or in a 2D space, nicely in a square block, right? And then you look at the center area. You look at a random base station at a location XY. Sorry, a random mobile at XY. The base station at the center, and you look at what is the signal power. So signal power is generally given by some fading, right? Some random variable of fading, divided by the path loss. So path loss means like how the signal degrades over the time, and that is generally given by x square plus y square to the power a. So this is root x square plus y square is distance, and the power a is called path loss exponent. Interference is similarly that way. So the total SIR will be this divided by I. Okay. But so you can of course compute it if you know the location of XY. But if I ask a probability question that what is the probability that if this XY is random, what is the probability that this ratio is greater than some t? Okay, for a random XY. So you look at this. You have H naught, this is a random variable, this is a random variable, XY is a random variable. So you have 5 random variables in a cell of just 3 base stations. Okay, and if you try to compute it, you cannot compute it on hand, like by hand. So you just do a simulation for this, even for this. So what is the problem with simulation? That you can get a result, but you cannot understand the dependence of the parameters over the answer. Okay, if I want to change density, if I suppose want to change the fading distribution, I have to redo a simulation and just check how the things changed, right? But you can never be sure the trend I am seeing will actually, we will see even when we increase. Suppose you change density, your coverage increased, right? You changed density once more, increased it, and you got one more increase. But you can never be sure that if I keep on doing this, you will always get a gain, right? So that is the one problem with simulation, and if we take this kind of approach, we can only do simulation. And you can see that this is the simplest model. A realistic model which generally people talk about has 19 cells in it. Okay, and then you talk about random variables here. There will be almost hundreds of random variables here, and analysis is really possible. And simulation doesn't give you the dependence between this and depending with the result and the simulation parameters. But we are not totally ignoring simulation. It's actually good when we want to characterize the performance to a number, right? Very accurate number when we have very complex channel deployments and correlation in channel, then we have to do simulation, and it's a good way to validate it. But for a system design perspective, it may be interesting to understand the underlying dynamics also. Okay, and that being said, what happened recently that in past we used to have this kind of pre-planned very nice kind of cell, but here we look at, this is a real 4G deployment for LSCT, and then you can look at these cells are not like this. They are not fixed grid. They have some randomness in it, and that is generally caused by space constraint. That suppose there is a lake, you cannot put a base station there, right? Then there are other issues also. So when you totally see at any realistic 4G deployment, it is not a fixed deterministic model. It has some randomness in it. And as we go to even more towards 5G, when we start having more number of small cells, these small cells can be user-centric. Means suppose there is a high density around a user, around a space, so you put more base station there. Then some base station can be actually deployed by the users itself, right? They can buy their own campus cell and can deploy it. Such kind of deployment actually results in a more randomized deployment. The location of the base station is not deterministic. It is located uniformly over the space in some randomized fashion. Okay, so that is the key part where people start looking at stochastic geometry. The underlying is that increasing randomness, base station location are getting more and more random over the space. There were, of course, as we discussed, problem with the simulation approach. And if we have some kind of tractability, then that can provide us some kind of insights to us, to a system designer, that should he increase density, should he increase beam weight, though, and we can also result in some quick conclusions also, rather than doing a full 3-4 days simulation. Okay. So mainly, what is stochastic geometry? Is study of random geometry, and it has been there for a long time in maths. It has been used in physics, chemistry. The one application was to understand how water molecule flows in a porous material. That is one of the standard application it had in around 1950 or something. But recently we started applying it into cellular network around 2010, 2011. There were a couple of papers in this. But now if you look at, I think there are like 10,000 papers on stochastic geometry in just 8 years. Okay. So it's an emerging field, and then people have applied it to different scenarios, right? Why? Because one, it provides tractability. As I said, you can get some expression. Sometimes it cannot, it's not in closed form, but still you can understand the underlying dependence. This is also important, that in the paper by Andrews in 2001, tractable approach to coverage, rate and coverage, they showed that if you actually take a deterministic model and plot the coverage, and then you take a random deployment and you plot the coverage for it, and then when you compare to a realistic model, both are not correct. Both are approximation, because real deployments is somewhere in between. And both has a 3 dB error in the performance. So by going to random geometry, you do not lose anything. You're getting the same kind of accuracy as you have got from a grid model, at least for this basic case, and you again gained in a form of that you got some kind of tractability. Okay, and this again suits better when you talk about small cell networks, and millimeter wave is going to be one of them, because you will put them lot of base station over the space. They will be very dense, as we see. So the stochastic geometry modeling is one way to go about it. Okay, and not only they can model base station and user location, they can also model blockages. Okay, you can also use them to model connectivity in a network. And previous application we had in cellular, it has been used for ad hoc network to understand Aloha protocol, some kind of transmission optimization. People have used it, and for heterogeneous networks where there are different types of small cells in a same network. So you have some LTE base station, some Wi-Fi cells, some parameter cell, pico cell, and in this overall network the user can connect to anyone. Here you want to talk about what is the coverage you can achieve. So that we call it heterogeneous networks. People have also used it in that area. Okay, so let me start with what exactly is small primer of different tools in Poisson point process. In a point process, and how we are going to apply it. Okay, so what is a point process? It's a random stochastic process, but instead of time, it is on space. Okay, so each realization is a deterministic set of points. Okay, and the overall point process is just a randomized version of that. That it's a process where each realization is just set of points. Okay, so number of points in an area can also be random. Okay, so this is just a set of different points, and the number itself is random. And there can be different types of point process. For example, this is a uniform point process. The base stations are located uniformly over the space. This is non-uniform. There are some base stations around the origin, but as you go away from origin, number of points decreases. This is some kind of cluster point process, where there are some hotspots and all base stations are there. Okay. So point process can also be represented by a measure, in the sense that you can also talk about average number of points in a set. So you have any set, and once you realize a points, you can always say that how many points fall in a particular area. Okay, so if it's a random, then number of points falling in a set A will also be random. Okay, it can have some fixed mean number or some kind of distribution over it. Okay, so there we talk about this expectation intensity method, which means that average number of points in any set area. Okay, this of course depend on the set. So if you increase the set, number of points will increase. Okay. Okay, then suppose each point, then there are two ways we can characterize this point process, because there can be different types of point processes. So one way to characterize this point process is evaluating a function over it. So suppose these are all points, there is a function which maps each location to a real number. Okay, so at each point you get a number, and I want to ask what is the total total sum of these functions. Basically sigma fxi. So you xi different points, and fi is the value at those points. You want to sum them and want to ask what is the expected value of those sum. Okay. This will be interesting to see that suppose each base station is interfering to you, right? So each base station, depending on the location, there is an interference coming from that base station. You want to ask what is the sum interference. Okay. So this fx will look like the interference coming from the base station at xi, and when you want to sum it, this will be the sum interference. Okay, and that can be computed by a simple integration over function multiplied by the density of the base station divided by dx. Density means how many points are there in a set A. Okay. Okay. Then the one more part is which we call functional. There are two different functionals which people use in stochastic geometry. One is Laplace, which is given by this. So again same thing, you go to each point, you compute a function fxi at that point. This point depends on the point process, right? So each relation you get new points. Okay. So in one realization you go to this each point, compute a function, compute a sum over it, right? Do exponential this, right, and just compute the expectation over different realization. Okay, and that will be a fixed number. So if the point process is fixed, is a particular type, this function is a kind of deterministic function, and this is also a characteristic function in the sense that if two point processes have same Laplace functional, this means those point processes are the same point process. Okay. Similarly, instead of Laplace, which is very similar, you can also compute product of a function values. So you go to each point, compute the function, compute their product, right, over all points, and then just take an expectation over different realization. Okay. So you go see one realization, you compute this, multiply by the probability of that realization, and you do with all one. These two functions are kind of characteristic. So second one is called PGFL. Okay. So depending on the point process type, you will have different kinds of Laplace functional. We will look at a basic, very simple point process, yet versatile. So this is the most common point process used in stochastic geometry for analysis of different wireless networks. This is called Poisson point process. It has two properties. One, that if you take any area, any set, number of points in that set is Poisson distributed. Okay. And second property is that you take two sets which are disjoint, number of points or distribution of points in each set are independent. Okay. So this has nice independence property that you just take two different sets, the number of points in the two sets are totally independent to each other. Okay. And each set, the distribution is Poisson distribution. So if I take a set A and I ask how many points are there, right? What is the probability the number of points in that set is equal to n? This is given by this distribution, exponential minus lambda a to power n by n factorial. That is in the form of Poisson distribution. Okay, and lambda A is the average number of points. Okay, so suppose I tell you that there is a set, the average number of points are 5, then on the average the number of the distribution of points in that set will be given by exponential minus 5 to the power n by n factorial. Okay, so just you have to compute what is the average number of points in a set, and from there you can get a distribution of the number of points in that set. Okay, so that is the definition, but in general what we get, this is kind of a uniform distribution, right? If you take any set and condition that you have 20 points in it, then all points are actually uniformly located over the space. Okay, so this is kind of a uniform distribution, that you take a set, you as condition on the fact that it has 20 points, all the points are uniformly located over this space. Okay, each point is uniformly located. Okay, but total number of points in this area is again random, is given by this Poisson distribution. But once you fix the number of points, the distribution of the points is uniform. Okay, so whenever you have a uniform deployment, that you have some number of base station and you deployed it over the space, you can use Poisson point process for that. Okay, so it basically looks like a uniform distribution over the space. Okay, so for example, take one case, the probability that there are no points in a ball S of radius r. So you take a set which is circular. Okay, it has radius r, so the area is pi r square. Okay, and density is lambda. Okay, so density means the number of points in per unit area, that is lambda. So the area is pi r square and the density is lambda. So total average number of points in that area is lambda into pi r square. Okay, so lambda is density, number of points per unit area, and area is pi r square. So number of points is lambda into pi r square. So that is your lambda A. And if I want to compute probability that the number of points in that set is 0, I'll just put n equal to 0 here, and you get exponential minus lambda. This is lambda pi r square. Okay, so the probability that in any set there are no points is given by exponential minus lambda into multiplied by the area of that set. Okay, so as you increase this ball, probability that there are points in this will go decreases. Okay, by this exponential amount. Okay, so we have two kinds of Poisson point process. Okay, so intensity is just a derivative of the average number of points in set A. Okay, you take a ball R, you compute how many points will be there, that is your intensity measure. But if you differentiate it, you will get lambda x. It's like a derivative of the measure. So basically what you should, intensity means if you compute the integration over density, you should get expectation measure, right? For example, if lambda is your density and you have area is pi r square, you just put lambda here, fix into dx, you get lambda is constant, lambda should come out, the integration over dx is just area, you get lambda into area. Okay, so if you talk about a uniform point process where the density is constant, right, you go at any region, you will find the same density, same number of points per unit area. In that case, we call that by lambda, and you multiply it by the area A, you get the average number of points in that set. Okay, in a non-homogeneous point process, this is not the case. The function lambda can itself be a function of x, right? So you can see here, the average number of points in this area is small, average number of points in this area is bigger. Okay, so as you change your location, the number of areas may decrease. Okay, so these are two types of process. Both are independent in the sense that you take two sets, the number of points will be independent to each other. Okay, but the density is uniform in one and density is non-uniform in the other one. Okay, and density we talk here is lambda, that is number of points per unit area. Okay, And for this, these are the mainly results. Laplace function of point process is given by this integration. So this exponential minus integration 1 minus e minus fx lambda dx. So if the function is given, you want to compute the summation of function, then the answer integration is this one. Similarly for PGFL, when you want to compute the product, this is given by this. So these are two main results which we mainly need to know, right? So there is a Poisson point process with some density lambda, with per unit area I know number of points. So this will be two main functions I need to know, right? And if I know this, I would be able to do most of the computation in stochastic geometry. Okay. This is called Laplace function. This is called PGF. Okay. Okay. So what is the benefit of point process? Poisson point process. So right now I'll mainly talk about Poisson point process. It's a uniform point process and is very suitable for wireless modeling. Basically because of multiple reasons. One, if this is a Poisson point process, this is another point process. If you add them, means you find a superposition of these processes. The point process you get is also a PPP, Poisson point process. Okay. So you take two different point processes. You find a superposition, combine those sets, the resultant you got is again a point process. Okay. Thinning means you have a point process, you go to each point, you flip a coin and decide whether you want to keep that point or not. Okay. You do it with each point. If you get a head, you keep it. If you get a tail, you delete it. Right. Resultant point process, whatever you get, is again a Poisson point process. Okay. So this is useful when suppose these are all transmitters, suppose these are all nodes, and each node decides on its own whether to be a transmitter or to be a receiver. Okay. So you want to look at only at the transmitter locations. So those transmitter locations will again be a Poisson point process because you are getting it by thinning of the original node process. Now displacement again, if you have a point process and you displace each point by a random vector, right, whatever resultant you get is again a PPP. Okay. So this is useful in modeling the mobility. You have some users, they move over time, right, the new location of mobile is still a PPP. Yes? Yes, this is not random, but this is again a PPP. Even if you do random, suppose you replace instead of 2, you put H, where H is some random variable, then still that is PPP. Okay. So yes, for this case, yes, base station is stationary and the users move. So the new location of user will still be, we can still model it using a Poisson point process. Okay. Of course, base station can also move. Suppose you talk about some kind of UAE deployments, then that can also happen, right? Huh? Yes. Depend on what kind of thinning you do. If you do a location dependent thinning, right, you get a non-homogeneous. Suppose you start with a homogeneous point process. Points are everywhere uniformly. And each point you do some kind of thinning regardless of where the location is. Then you get a homogeneous. If you do a thinning based on the location, that if point is far from the origin, then you do not keep it with high probability. Then you get a non-homogeneous point process. So density will change, yes. All will be Poisson point process, but the density you have to compute, that will depend on thinning probability, that will depend on how you are displacing it or how you are superpositioning it. Okay. So that is these three things are a good reason why people came with this. For example, frequency reuse, right? There are some base station and few base station uses frequency 1, other base station uses frequency 2. So you only get interference from the people who are using the same frequency as you. Other you can ignore, right? So when you look at around you, both base station are using frequency 1, they look like a thinned version of the original base station's location. Okay. So there you can also model frequency reuse using thinning. Okay. So let us look at a very simple example to understand how we apply, right? I take a very simple case, ad hoc wireless system. There is a base station, there is a UE here. Okay, so I found a random UE. Okay. Now this model says that you have pairs of base station and UE. This model, this ad hoc network is made from pairs of base station UE. Each pair has one base station and one receiver. They are fixed. You are not changing it. At a distance, fixed distance r. Okay, so that distance is fixed. Now you just consider a random pair, right? Random pair, and assume, because this is homogeneous, stationary, you just assume the receiver is at the origin. So you take that receiver, his base station is located at distance r, that is fixed. For every UE, the base station is located at, their base station is located at distance r. But the interference can be anywhere around it. Okay. I assume a fading which is exponential, Rayleigh fading, so the power is exponentially distributed. So H is just exponential with mean 1. I assume for this case just unit transmit power. So path loss, if the base station is at distance x, the path loss is some function of Rx. For here, this case we model as x to power minus a. Okay, distance is x, so x to power minus a is path loss. That is my path loss. Okay, so the received power from any base station is actually given by fading multiplied by that path loss. Okay, where xi is the location of the base station. I want to compute the interference at the receiver. Okay, so if you look at the interference at the receiver, it is summation from all the base stations which are not serving. These base stations are located as a Poisson point process. That was our assumption. We assumed a uniform distribution. Fading multiplied by path loss exponent. Okay, and this is one more important thing. The base station who is transmitting is not included in it. Okay, you do not include the power from the serving base station into interference. Okay, but that is one of the key point of Poisson point process, that even if I remove a base station from a Poisson point process, the rest of the process is still a Poisson point process. Okay, that is because of the independence property. We said in two sets, the Poisson process is independent. So you condition on this point and look at whatever the distribution of rest of point, that is still a Poisson point process, right? So you can remove some points from the Poisson point process, or you can add. It doesn't change the distribution of Poisson point process. And that we call Sirnak theorem, and this is the key concept why people keep using Poisson point process. If you take any other point process, this independence assumption is not satisfied. Okay, in fact, Poisson point process is the only point process with independence property. So there you have to find the distribution of the rest of the base station, right? And that may become sometime tricky, but it's not that difficult. People have also looked at it. But this tutorial we will look at Poisson only. So as I said, I removed this base station, rest of the base station still look like a Poisson point process. Okay. So let us see how I compute the Laplace transform of the interference. Okay. Once I compute the Laplace transform of interference, I can know the whole distribution of it. Okay. So what I am interested in is computed e to power minus si. That is the Laplace transform of interference. And I is just the sum. Okay. I is given by summation over hi xi minus alpha. Okay. Fading multiplied by the path loss, and you add it for all points. Okay. So this expectation is over point process location and also over all fading. Okay. So we can separate this expectation over two random variables, fading and this thing. And what you get is the point process expectation is outside, and the fading expectation I took it inside. Now if you look at this, this is e to power minus hi multiplied by something, an expectation over hi. Okay, So this is nothing but the moment generating function of exponential random variable. If t is a random variable, then h is a random variable, then e to power minus th, h is exponential random variable, is given by 1 upon 1 plus t. Okay. For any h exponential random variable, this is given by 1 upon 1 plus t. And this is very similar. H is there and the rest you can see at t. Right. So you get something like this. Now this is very similar to the PGFL we saw. Right. PGFL was product of functions, right, over location. And if you look at this, this is a whole is a function of xi. Okay. And you are computing a product over it and the expectation over different realization. So you can apply directly the PGFL of Poisson process because xi is a PPP. And this is the expression we wrote earlier. This is the PGFL expression. So you just take the function 1 minus fx and you integrate it over the density. So what I got, I just took this function and put it here, right? So this function is fx. So this 1 minus fx and then integration over lambda dx. That is my Laplace function of interference. Okay, and you can convert. You can further solve it, convert to a polar coordinate, right? Finally, you get an expression like this. So this is exponential minus lambda pi s2 by alpha and some constant. This depends on path law experiment, but these are just constant. So this is minus pi lambda s2 by alpha into some constant, right? So you can see Laplace interference depends on the density exponentially. If I increase density, the interference will decrease by exponentially, right? Now the next part is how I compute the SIR performance. Okay, serving power, the base station is fixed location. Base station is located from the user at a fixed location R. Okay, so the serving power is given by some fading multiplied by path loss, which is R to power minus alpha. Okay, so your SIR is this power divided by your whole interference. Okay, and I am interested in finding SIR coverage. SIR coverage is probability that SIR is greater than some theta. What is the time? 10:30. Okay, so we have until 11:10 for this one. Okay. Did you get this, right? So fading multiplied by path loss here is fixed, R to power minus alpha, because base station user density distance is fixed. So you get this, I divide pi interference, and I wanted to ask what is the probability that this SIR is greater than theta. It's a random variable because interference is random, signal power is also random. So you just write it here, signal power divided by interference greater than theta. Okay. So you can multiply, I take I here, theta I, you take R by alpha here. So you get H greater than I theta R alpha. Okay, just multiply it here. H is an exponential random variable that we assume, and probability that the exponential random variable is greater than something is exponential minus t. Probability that H is greater than t is exponential minus t. That is distribution of exponential random variable. You put it here, you get something like this, exponential minus I theta R alpha. If you look at this, theta and R alpha both are constant. So this is some constant multiplied by I and expectation over interference. This is nothing but exactly the Laplace functional of interference, right? So this is equal to where S is this part. So you get Laplace functional and S is theta I. So there should not be an I. This is just Li theta R alpha. Okay, where S is given by theta R alpha. And we have already computed the Laplace function in the previous part, right? This is LIS. So what I have to do, instead of S, I have to just put the new value, right? Just put theta R alpha here, and I get the SIR coverage, which is given by this expression. So if you look at it, this is minus pi lambda theta to the power 2 by alpha R square and then some constant. Okay. So you are actually able to get a closed form expression of SIR coverage in a random network. Okay, this is no way possible in simulation. And you can actually see the dependence also, that this decreases exponentially with lambda. If you increase theta, then 2 by alpha, with that the probability will decrease, so you can actually plot it. And then if you increase density r, again this will, so if you increase that distance between base station and the user, you will lose, right? So how can it help? Suppose a system designer come and ask, hey, I have to deploy new pairs, right? So that my density will double. Okay. Right now I have 100 base station receiver pair. I have to make it 200, right? But I want to keep my SIR coverage same, right? Then what should I do with the distance of the transmitter receiver pair? So you can look at this expression and say, if lambda r square is constant, then you will get same coverage. Since you increase lambda by 2 times, you should decrease r by root 2 times, right? If you do that, you will get the same coverage, right? So this kind of simpler insights you can get from that expression. And if you ask the same question by simulation, he will do multiple simulation and try to keep different r and try to look at which r give you the same kind of distribution. Okay. So, but again, when you actually deploy, so I'm not totally denying the benefit of simulation. When you actually deploy a network, there are other issues. You also want to look at, include scheduling into it. You also want to include different correlation, building and everything like that. So there you need exact number. There simulation will be helpful. For the pre-stage, when you're just looking at how I should choose my parameter, the analysis is a very good tool for that. Okay. So that is the end of this primer. If you have any question in this, you can actually ask right now. Any question in stochastic geometry and like that. Yes, generally, one way people model is using superposition of different point processes. So the LTE base station we also model with a point process with a lower density. Then femtocell maybe with a higher density you model it. And the powers are different, the antenna strategy may be different. So when a user is located somewhere and he want to connect, right? So he can connect to any of the base station, be it LTE or femtocell. So he kind of computer receive power and find the best one, and he connect to that base station, and there you define. So basically which we call classes, right? So if they base LT and a femtocell, they are called 2 tiers or 2 classes, right? And the superposition will be again a point process, right? But you can look at as this each class is the thinning of the original point process, right? Original point process is a mixture of both base station, and each base station can be LTE or femtocell independently. It's like a thinning of the original one, right? So that way you can model. There has been a lot of work over that. Again, it requires little bit more work because you have to then talk about association probabilities, that what is the probability that you connect to the small base station or a LTE base station, and then condition on that you have to compute coverage, and then you add the coverage from all kind of classes, something like that. Yes. Yes, for example, here it is very easy. Suppose rate you take as log 1 plus sin r, right? So probability that log 1 plus sin r is greater than r, right, is equal, you can do a transformation and find that this is equal to the probability that sin r is greater than 2 to power r minus 1. Okay, log 1 plus sin r greater than r means sin r is greater than 2 to power r minus 1. Okay, which is same as this. You just instead of theta, you put 2 to the power r minus 1, you compute the rate coverage, and then you just multiply lambda to it. So you get the number of density for that, right? Rate coverage you can compute, average transmission you can compute, right? You can also compute what is the density for which you get at least some minimum density. You can actually compute also, so sometimes what happens, some base stations do not transmit all the time, they transmit with a probability P, right? So the active base stations is again a PPP because of the thinning, but with a density lambda P, right? So suppose they only half of the people transmit with half probability. This means the density of active transmitter is lambda by 2. If 1 by 3 people transmit at any time, then density is lambda by 3, right? You can just put it here. Instead of lambda, you put lambda P, right? And then you can optimize it to compute what P I should choose so that my SIR coverage is maximum. Because when you take high P, right, you get more interference. So your SIR coverage decreases, right? But you get more transmissions also. If more people are transmitting, you get more transmission density, right? But many transmitters will be unsuccessful. So there is a trade-off between the two. If more people transmit, but there is a higher unsuccess probability, then you also do not get gain. You want to increase up to a limit such that interference is not that much and you still get a decent coverage. So some kind of optimization problem can also be found once you get this expression to optimize few parameters. You have multiple operators, suppose, right? Like when you talk about spectrum sharing, you have Airtel base station and Vodafone base station, suppose. And you want to ask, what, in that scenario, when they start sharing spectrum, right, what will your coverage will be? So that is one other example where you talk about the superposition of two different types of networks, same type, but of different administration. So you have to take care of so they will be like that, superposition. Same band, yes, same time they are using. So we will actually have some discussion over it. Both operators are using same band, same time, without any coordination. Okay. But again, if you have some coordination, that can also be done. That can also be analyzed, right? Some kind of CSMA kind of sensing can also be analyzed. So it has very wide application. If you look at it, right now I told you that it started with 2 papers in 2010. Right now there are 10,000 papers on stochastic geometry. People are discussing random ad hoc networks, head networks, uplink processes, right? Spectrum sharing with different models, cognitive radio, carrier sensing, all kind of things are there. So I had also, I can actually share in the slides also. So there is also a paper by me, it's called Primer on Stochastic Geometry, which also lists a lot of other research area in this and what we can learn. So we mainly discuss about cellular networks, uplink network, and a heterogeneous network. Okay, we discuss 3 main systems: cellular system, uplink cellular system, and heterogeneous network. And then we mainly talk about different tools we will need, and then we give a list of all other fields which we can look at. Right? It's called Primer on Stochastic Geometry. So we come to the third part, how we can now use the whatever we have learned from stochastic geometry here. Right? So what we did is a short one. Yes. Yes. What do you mean? So the underlying process is a Poisson point process, right? When you start, when you deploy nodes, all the nodes, secondary or primary, are Poisson. But at a particular location, you look at that depending on the other base stations, if you have someone primary transmitting or someone in the closed vicinity, you do not transmit, right? So then you do a thinning, but that is a dependent thinning. So the new point process is no longer a independent process, right? That is called Martin hardcore process. Okay. So there also, but the original underlying process is a Poisson point process. So using the tools from there and some kind of thinning, you can still derive the results of cognitive radio. Okay. But when this is not valid, when you have some kind of repulsion in the or attraction in the point process. For example, you put base station such that there is a minimum distance of 50 meters among two base stations, right? Then the Poisson point process is not a valid point process, right? Or you want to put two base stations at the same location, then normal point process is not a valid one, but we found there is some derivation we can do still there. But that being said, we should also consider that base station location is one point, but how receiver look at them is another question. Between user location and the base station location, there is a channel, there is shadowing, there is fading, everything is there. So eventually the receiver looks at the location as a randomized version of the original base station location, right? Suppose this base station is very close to me, that base station is very far to me, but there is a tree in between, but there is no tree here. So this base station actually looks to me that he is very far because the receive power is very low. In that case, how the user looks at the base station location is very dynamic. It's totally random, right? And you are concerned about how receiver looks at the location, not what their actual location is, because we are mainly talking about the coverage performance, the receive power performance, right? So there is a result by Hangi also, and there is another professor by Bartek Killer. They said that in presence of enough shadowing, right, each point process looks like a Poisson point process. Even if it's a deterministic process, like a grid process. You put base station in a grid, right, but you have enough shadowing. Then the actual process which the receiver looks at is the Poisson point process. Okay. So that gives a very strong result in this, and which validates also that Poisson point process is actually a valid model, even when we are talking about deterministic models or pre-planned models. Okay. Huh? NF shadowing means yes, kind of. That result is particularly I don't know, but if you have less, then you will get some error. We can still represent it. So this, whatever the bound they have shown, is approximation. It says that as you increase deviation, then of course you get more close to Poisson point process. Again, depends on density, right? But exact number depends. I don't know. But there is some theoretical results about it. Okay. So in this part, we mainly talk about how we use whatever we have learned only to millimeter wave networks, right? So what I assume here is base station are modeled as a Poisson point process, is a small cell. They will be very dense, okay? And we are not talking here about very dense network. We are talking about normal deployment of a suburban or rural setting, okay? So the base stations are, but this model can be again adapted to the dense networks also, with some changes. And then users are also modeled with a PPP with different density, okay? So again, to remind you, sorry, this is with lambda. Again, lambda density means that they, on the average, they are lambda base station per unit area. So if you talk about 100 meters square, number of points on the average will be lambda into 100. Okay. Okay. So now we talk about, so this is one part. We talk in the end how base station deployment can be modeled. We can model it as a random point process. Then question is, as someone asked, how we model multiple operators, right? And this is very important because we will let you show later that spectrum sharing is going to be there for millimeter wave because they have very low interference, right? So people will be transmitting on the same band, so it is very important to model how multi-operators can be there. So this is operator 1, this is operator 2, and when you add them, you get a joint network, forget about this figure. Basically you have m different operators. Each operator is a Poisson point process with some density. Suppose they were deployed independently, then what you get is a superposition of those networks, right? What this figure shows is, suppose there are some base stations from network 2, and there are some base stations which are co-located. So they are leased by some other third party, right? And each towers, both operators are there, right? So this you can model, the combination you get something like that. Some are base station 1, some are base station 2, some are co-located, okay? This can also be modeled by superposition of 3 different PPPs, one with network 1, lambda 1, lambda 2, and this will be lambda 1, 2. You get a total network density lambda 1 plus lambda 2 plus lambda 1, 2. Okay. And if this is totally co-located, then you can just assume this one. If this is partially co-located, then you take all those things. And if it's just independent, then this density will be 0. So this particular case is somewhere between the total independence operators density and full co-location density. Okay. So, but here the catch will be when you actually talk about these things, the interference is sometimes correlated. For example, if your user associates with this, right, he still gets a interference from a site at the same location. Right? So X is there, right? So you can see if there is some signal power, you also get approximately same signal power as an interference. Okay. Okay. Then how we can model with LTE? So superposition of 2 networks in different bands can be either modeled independently, that there are some big towers, there are some small towers, and each are co-located, or you can model as a clustered process also, where these big base stations, LTE base station, are the center of the clusters of radius r, and all the other small base stations are located in that density r. Okay. So for this we have to use clustered processes, right? So there are different kind of processes again there. For example, there is one process where their clusters locations are still Poisson point process, and the radius of this is a Gaussian random variable. Yeah, I think something like that. But there are a lot of other processes. Again, analysis becomes a little bit complicated, right? So we will not cover it here, but there's of course references for that. Okay. So and there are other models, for example, also in stochastic geometry, lattice models where the base stations are actually located on the lattice, a little bit distorted from the center of the lattice. User-centric models where you have some hotspots and you want to put users on near to those locations, right? So in that case, you have to deploy base station based on the user densities, right? Then other models which are not analysis are 3GPP standard configurations. Like if you look at the document, recent one, they talk about different kind of deployments, which are actually very hard to analyze. Second part, blockages, right? So I also cover, what's name? Okay. So we again talk about different modeling, second part was blockages. So we also said that it's very crucial to model those kind of blockages, right? So Here we use Boolean process. It's a kind of a point process, mainly that centers of this process are still Poisson point process, but at each center you put a random object, right? This random object can be, for example, all lines, right? All are lines with some random orientation or length, or they can be some rectangle with some orientation, some length and width. They can be of different shapes also, for example, circles or other kind of prism and all those things, right? So this is again, we are using stochastic geometry to model such kind of blockages. So let us take how we can use it. Similar analysis but little bit different. Let us consider a link of length r, right? So suppose the base station is here, user is here, there is a link, and we want to understand what is the probability that this link is not blocked. Okay. If this link is not blocked, the connection will be line of sight. If it is blocked, then it will be non-line of sight, right? What we assume, the centers are located as Poisson point process. Again, this is same as uniformly located with density mu. Buildings, we assume for this case are linear, right? So each building is in a form of line, which no width but length, which length again is a random, which comes from a uniform distribution. Lmax can be the high maximum length of the buildings, right? So these parameters you can get from looking at the city. You get the city data and then try to find what should be the maximum length, right? And there again random orientation, you can assume that these are located in 0 to 2 pi location, right? But other kind of distributions are also possible, you can consider. They can also assume that they are all fixed length and fixed theta. That is also possible. And you want to look at the probability that a link or length of length r is non-blocked. Okay. So how we can compute it? Let us first consider only the blockage with length L and angle theta. Okay. So blockages can be of any length or angle theta, but let us just first consider the only a set of blockages with length and an orientation theta. Okay. So this is the link. This red one is the link between user and the base station. Okay. And I want to ask, where should the center of these blockages be such that none of the blockage intersect this line? Okay. If that is the case, then the link will be non-blocked by this kind of blockages. So you look at that, if the center is located here, this is a parallelogram I made with length L, angle theta and width r, right? If the base station, the blocking center is located outside this wall, it will not intersect. If it is at center, it will just barely touch, but if it is inside this, this will surely cut the block. So cut the link, right? Intersect the link. So what we get is that if any blockage is outside this parallelogram, right, then the link will be non-blocked. Okay. So the probability that the link is non-blocked is equal to the probability that there is no blockage inside this parallelogram. Okay. There is no blockage center inside this, right? And blockage center again is a PPP, and we derived the result in the past that probability that there is no point in an area A is given by exponential minus lambda A, right? That is from Poisson distribution. In a set area, number of points is a Poisson distribution. It is 0 with the probability e to power minus lambda A, right? So what is the density? So lambda means density of the PPP, right? So what is the density of these blockages? So note that we are only considering blockage with length L and orientation theta. Okay, not the all blockages. So this density will be smaller, right? So whole blockage is some PPP with density mu, right? And the blockage with length L and theta can be seen as a thinned version of the whole blockage process, right? You only consider those blockages which has a length, length L and theta. Okay. So probability that any base station has length L. suppose is given by FLDL. Okay. Suppose the probability that any blockage has length L is given by FLDL, and the probability that the blockage has orientation is given by F theta d theta. Okay. Then the density of this blockage process is mu multiplied by that probability. That we said, right? So basically it means that suppose there is a 20% probability that the blockage length will be 5, right? There are 100 blockages, and the probability that the blockage will be of length 5 is 20%. Then how many blockages will be there of length 5? Basically 100 multiplied by 20%. So basically 20 blockages will be there with length 5, right? So same thing as we did here. So there is a total density, and we multiply by the probability of the blockage having L length and theta length. Okay, you get the density of the blockage this with only length L and theta. Okay, once you get that, this is my density. You need the area of this. The area of this is given by L into R into sine theta. Okay, so the probability that there is no blockage inside this, no blockage center inside this, is given by exponential minus density multiplied by the area. Okay, is that clear? So we get something like mu FLDL, this is the density, this is area. Now the probability that link is not blocked by any blockage, okay, of any length or theta, will be just multiplication of all probabilities, right? That is not blocked by length L, it is not blocked by length L2, it is not blocked by length L3, and you get something like this. This product you can take inside and this become integration for a discrete, for a continuous case. You get something like this. This is the integration over L sine theta over distribution of L and theta, basically expected value. You compute it, you get EL multiplied by E of sine theta, which is 2 by pi. So this is the expression you got, exponential minus mu multiplied by the length R into expected blockage building length multiplied by 2 by pi. Okay. So if you see this whole thing, if you take R out and take mu, EL and 2 by pi, call it B together, right, you get something called e to power minus d by B, where B is just pi by 2 EL into mu. Okay. So what you get, R. So we had, the length is R. So the probability that the link is blocked, of length R is blocked, is given by e to power minus R by DRS. Okay. DRS is just a parameter which depends on the expected building length and the building density. Okay. So in this way you can find that what industry uses can also be proved by analysis, right? If you take a random geometric broadening model, you can also get the same probability. His building is length is blocked is exponential probability, but you also get a relation. If you know the building density and the expected length, you can compute the probability of a link to be blocked. Okay. So this expansion something like this, 1 upon B somewhere else, and somehow 1 upon B also reflect the average line of sight region, right? For example, if B is 0.07, 1 upon B comes out to be 140 meters, which means that on the average you will find that all the links which are inside 140, so beta, is here, exponential minus beta r. So this is what you got. So if I know beta, 1 by beta gives you the average line of sight region. This is defines like 140 meter means on the average you can expect that in this blockage scenario at 140 meter you will see a line of sight link, and after that you start having lots of non-line of sight links, right? So this gives you one insight that your serving base station should be at least less than this distance. Should make a deployment such that lambda should be like closest base station should be less than 1 by beta, something like that, so that you get at least one line of sight link. Huh? Yeah, yes. So by looking at this and lambda, you decide a cell radius, right? you can achieve one if you, so again, you can achieve some kind of probability. When you talk about what is the probability that you at least see a line of sight base station, you can compute from this, right? And then so you can integrate this with the distribution of R. R is the, suppose, and you get a probability, and from there you can see a relation between lambda and beta. How I can actually do it? So this, I say the probability that a link is blocked is this, right? So I want to compute probability that a serving link is blocked. Now serving link is the closest base station. You can compute the distribution of closest base station and average this probability out with the distribution of R. You get the probability that the serving base station is blocked, and that will be a function of both lambda and beta. From there you can see a relation. Okay. So next part, you can also talk about rectangular blockages. Instead of lean lines, you can talk about rectangles. Again, you can form the same kind of geometry. Instead of the parallelogram, I have this extended parallelogram where the blockages should not be there. If the block is centered inside that, then this rectangle will surely intersect the link. Okay. And the probability in this case is given by this. So you get an additional P term, which is a constant P, right? And that is, so B is again given by same thing, but instead of just EL, you also have EW, which is the expected width, right? So this 2 EL plus EW is the expected parameter. 2 multiplied by EL plus EW is the expected parameter of the building. If you know expected parameter of building, you can put just directly there. And second is, this is EL into EW is expected area of the building. With these two parameters, you can compute these two methods, and the final expression will be given by this. Okay, any question in that? And then you can also put like circles. People have worked on circles. There's some work by Kiran Venugopal and Robert Heath, which talks about you can block, model blocking using the circles for other networks or something, polygons, something like that. But this was a very versatile model. Then people also talked about it. Instead of this, you can also talk about other kinds of line of sight models, and people have also validated it with different building models. Okay. So how we can incorporate this, right? So suppose a user is at the origin, right, and the base station is all located around it. He looks at any base station, find its distance, right, and compute the probability that this link is blocked or not, right. He does it for all, right. So finally, for each base station, you know whether that building is blocked or not, right. So now you separate this out. For each set of base station, you separate out the base station which are line of sight and separate the base station non-line of sight, right. Each one is a thinning version of the original one, okay. Independent thing, we assume, for this case, we assume an independent blocking, right. If you do not assume it, then this is not possible, okay. So, but people got independent blocking. This is true for suburban case, which we have shown later in other paper. But for dense urban case, it may not be true. But for normal case, we can assume that thinning is independent, means a computation whether a link is blocked or not is independent. You get a line of sight base station link and a non line of sight base station link. Again, the probability that the line of sight TI is given by lambda multiplied by the probability of thinning, right? We are thinning with the probability PR, where R is the distance from the origin. So the probability will be given by lambda into PR. Lambda is the original density multiplied by thinning probability, which is PR is a line of sight probability. Okay, and line of sight will be 1 minus PR. If you 1 minus P line of sight, and you get this thing which is called lambda into 1 minus PR. Or you can also say, instead of 1 PR, you can also write P non-line of sight, which is again equal to the probability 1 minus probability of line of sight. And again, we can have different path models. For line of sight, I assume the path loss is given by some gain. This is called near field loss multiplied by x locate distance into alpha L. Alpha is line of sight path loss and CL is the line of sight near field loss. Similarly, for non-line of sight, you have a different path loss exponents, and these are actually can be seen from measurements, right? So there is some measurements and by Ted Rappaport group and other people who talked about how we should choose this kinds of path loss exponent differently for each alpha and this thing. What we took is around CL is minus 60 dB, this is around minus 70 dB, and the path loss exponent is around 2.2 and non-line of sight is 3.3, something like that. That was standard we found, but people take different deviation depending on different models they are talking about. So this is the last one before we break. How it will result? So this will look like line of sight base station, right? Because the probability is PR decreases with R, right? So this is thinning, but you get a non-homogeneous point process because as you go from away from origin, the probability that the link will be blocked is high. So you will not see a line of sight base station at a distance. Where this has a gap here. It shows that at very close distance, there will not be non-line of sight base station, and you will, as you go up, all the base stations will be non-line of sight. Okay. So let's take a break here, and then we will add after that.
Thank you, Dr. Gupta, for the wonderful session. So we'll reassemble here at around 11:40. There is coffee outside, so please.